Build a tiny language AI from scratch. Part 4, the finale. Generation, generalization, and a genuinely surprising answer. Training is over. The weights are frozen. Using the network is now just the forward pass. Encode 2 words as one hot vectors, push them through W1, ReLU, W2, softmax, and read off the probabilities. For the sky, it might say, is 72%, blue 5%, bright 4%. Argmax picks the winner. The network has become a function you can simply ask. One word isn't a sentence, so we loop. Start with the sky. Predict is. Append it. Now take the last 2 words, sky is, and predict again. Bright. Append. Now, is bright predicts the end token, and generation stops. The network itself decided the sentence was finished. This is autoregressive generation. The model's own output becomes its next input. It's the same fundamental loop that modern language models run, just with a 2-word memory instead of 100,000 tokens. Let's talk to it. We type, the sky. It answers, the sky is bright. All 3 sky sentences were in training, and this run happened to rank bright highest. We type, AI can. It answers, AI can predict, also learn directly. We type, people can, and get, people can learn, straight from the training data. So far, impressive memory, but only memory. Then we type something different, Python programming. And it answers, Python programming can learn. Stop and check the training data. That sentence is not there. Not even Python programming can. The pair, Python followed by programming, never appears anywhere in those 38 sentences. A lookup table would have returned nothing, because the key doesn't exist. Our network produced a grammatical, even sensible continuation for an input it has never seen. How? Because it isn't looking things up. Each word carries its own learned influence. Python appeared in training. Python is useful. Python is powerful. Programming appeared too. I like programming. We like programming. With one hot inputs, the matrix multiply effectively selects the learned row for Python in the first position, and the row for programming in the second, and adds them inside the hidden layer. That combined pattern is brand new, but its ingredients are not. It leaned toward can. Then the context, programming can, hit training's strongest pattern. Can leads to learn. 2 known effects combined in a way nobody taught. That is generalization. Before we get too excited, let's be honest about the limits. When it generated that final word, its entire context was programming can. It had already forgotten Python. Our model only ever sees 2 words back. And try banana programming, you may well get banana programming can learn, which is nonsense. The network isn't checking meaning against reality. It's combining learned numerical patterns, whether or not the combination makes real-world sense. Generalization is not the same thing as understanding. That distinction matters for our 40-word toy, and it still matters for the largest models in the world. So what did we actually build? Sentences became tokens. Tokens became numbers. Numbers flowed through 2 grids of weights. A loss measured the mistakes. Backpropagation assigned the blame. And gradient descent turned 5,000 rounds of correction into behavior that occasionally surprises its own author. Now, break it. Change the training sentences. Shrink the hidden layer to 8. Cut the epochs to 500. Type strange word pairs and watch what happens. That intuition is the real prize. Next series, word embeddings, where words stop being isolated slots and start having relationships.